Implementation of Polaris Spaceplanes Reusable Launch System by 2025. Overview. Polaris Spaceplanes, a pioneering aerospace startup established in Germany in 2019, is set to revolutionize access to space with its innovative project AURORA. This ambitious initiative aims to marry aircraft and rocket technologies to create a reusable space launch and hypersonic transport system targeting operational capability by 2025. With a budget allocation of €50 million, Polaris is focusing on advanced propulsion systems and a modular design approach to ensure flexibility and efficiency in space travel. Key development phases. 1. Initial research and development. The groundwork for AURORA builds upon over 3 decades of rigorous research in spaceplane technology conducted at the German Aerospace Center (DLR). This phase includes essential studies and the design of scaled flight demonstrators that will validate key technologies. The research aims to overcome the challenges of creating a vehicle that can operate in both atmospheric and space environments. Leveraging lessons learned from past European spaceplane programs. 2. Demonstrator testing. Polaris has made significant strides in testing progressively larger demonstrators. The latest models MIRA 2 and MIRA 3, each measuring 5 meters in length, are critical for assessing propulsion systems. A pivotal achievement occurred in April 2023 when Polaris secured a contract to develop the AS1 linear aerospike rocket engine. The culmination of this effort was marked by a successful in-flight ignition test of the AS1 engine in late 2024, validating its capabilities for future applications. 3. Hypersonic Research Vehicle Contract. In February 2025, Polaris landed a significant contract from the Federal Office of Bundeswehr Equipment Information Technology and In-Service Support (BAAINBw). This contract tasks Polaris with designing a fully reusable hypersonic research vehicle. Intended for dual applications, serving as a hypersonic testbed for defense purposes and functioning as a small satellite launch system when outfitted with an expendable upper stage. This contract not only signifies a critical step in the development of AURORA but also indicates the vehicle's potential contributions to both scientific exploration and national defense. 4. Operational deployment. The final development phase aims for the operational deployment of AURORA by 2025. This phase will establish a new standard in space transportation and hypersonics, enabling routine and cost-effective access to space while significantly enhancing the capabilities of hypersonic flight. Budget allocation. The €50 million budget is specifically allocated for 2 primary areas of development: advanced propulsion systems and modular design. The focus on aerospike engines, which offer improved performance in varying atmospheric conditions, is crucial for the success of the AURORA project. The modular design approach allows for adaptability in various mission profiles, enhancing the operational capabilities of the spaceplane. Key points. Pioneering technology. Polaris Spaceplanes is at the forefront of developing the AURORA project, integrating decades of research into a practical solution for accessing space affordably and safely. Reusable technology. The emphasis on reusable technology aims to reduce the costs associated with space launches and improve overall safety, potentially transforming the aerospace industry. BAAINBw contract. The recent contract with BAAINBw highlights the dual-use capability of the AURORA vehicle, emphasizing its roles in both scientific research and defense applications. Demonstrator validation. A series of demonstrator tests serves as a critical pathway to validate the technologies that underpin the AURORA project, ensuring reliability and performance upon deployment. Timeline of events. 2019. Polaris Spaceplanes is established. April 2023, contract awarded to develop the AS1 linear aerospike rocket engine. Late 2024, successful in-flight ignition of the AS1 engine. February 2025, contract from BAAINBw for designing a reusable hypersonic research vehicle. Development of AURORA officially initiated with plans for operational deployment by 2025. Differences between sources. Source 1 emphasizes the contract with BAAINBw and its implications for the AURORA project, including a detailed timeline of the development and testing of the AS1 engine. Source 2 provides a broader overview of Polaris's mission and the technological innovations involved, focusing on the integration of research and development efforts. Source 3 primarily highlights career opportunities at Polaris, indicating its growth and the recruitment efforts necessary to support its ambitious goals. Conclusion. The implementation plan for Polaris Spaceplanes' AURORA project represents a significant advancement in the field of aerospace transportation and hypersonic research. By leveraging decades of research, securing strategic contracts, and focusing on innovative technologies, Polaris is poised to make a substantial impact on how we access and utilize space in the near future. With a clear roadmap and a commitment to excellence, the team at Polaris Spaceplanes is on track to deliver a groundbreaking solution for both the commercial space industry and national defense sectors. The implementation of Polaris Spaceplanes' reusable launch system by 2025 is built upon a foundation of extensive research and a strategic development plan, which may include some counterintuitive aspects regarding budget allocation, technology integration, and the dual purpose of the vehicles being developed. 1. Budget allocation versus advanced technology development. The €50 million budget allocated for the AURORA project may seem limited given the ambitious nature of developing a reusable hypersonic transport system. Typically, such advanced aerospace projects require significantly larger investments. However, Polaris is leveraging over 30 years of prior research at the German Aerospace Center (DLR), which allows them to utilize existing knowledge and technology to reduce development costs. This counterintuitive approach suggests that prior foundational research can effectively minimize financial outlay while accelerating innovation. 2. Integration of aircraft and rocket technologies. The AURORA project aims to integrate aircraft and rocket technologies in a manner that is not commonly pursued in aerospace development. Many aerospace companies focus on either traditional launch systems or hypersonics. But Polaris's strategy of blending these technologies could yield unexpected efficiencies and operational capabilities. This fusion challenges conventional wisdom that treats aircraft and rocket systems as distinct categories, suggesting that hybrid systems can offer novel solutions for space access. 3. Dual-purpose vehicle design. The vehicle being developed under the BAAINBw contract serves a dual purpose, as a hypersonic testbed for defense applications and as a small satellite launch system when equipped with an expendable upper stage. This dual functionality may seem counterproductive at first glance, as it complicates the design and operational parameters. However, this strategy can lead to greater utilization rates and reduced costs per launch, as the same platform can serve multiple markets and needs, thereby enhancing the overall economic viability of the program. 4. Progressively larger demonstrators. The strategy of testing progressively larger demonstrators like MIRA 2 and MIRA 3 may appear to be a slow approach, as it involves multiple iterations before full-scale deployment. However, this methodical progression allows for comprehensive validation of technologies in real-world conditions. Each step not only informs the next but also mitigates risks associated with jumping directly to full-scale models. This deliberate pacing stands in contrast to the fast-paced high-risk approach often taken in aerospace projects, illustrating that thorough validation can lead to more reliable end products. 5. Focus on reusable technology. The emphasis on reusable technology may seem like a standard practice in modern aerospace. However, the level of integration and innovation Polaris aims to achieve with AURORA is noteworthy. Many companies have focused on reusability but often face challenges in operationalizing these systems effectively. Polaris's approach, which combines advanced propulsion systems like the AS1 aerospike engine with a modular design, suggests that they are not simply following trends but are instead rethinking the entire paradigm of space transportation. This perspective challenges the notion that reusability alone is sufficient, rather it necessitates a holistic approach that encompasses design, propulsion and operational strategies. In summary, the development of Polaris Spaceplanes' AURORA project illustrates several counterintuitive elements that challenge traditional paradigms within the aerospace industry. By leveraging existing research, integrating diverse technologies and focusing on dual-purpose functionalities, Polaris is positioned to redefine space transportation and hypersonic research while operating within a constrained budget. These aspects highlight the innovative strategies that can lead to significant advancements in aerospace capabilities. In examining the implementation report for Polaris Spaceplanes' reusable launch system, there are several critical aspects that most readers may overlook. Yet they hold significant implications for the project's success and its impact on the aerospace industry. 1. Integration of aircraft and rocket technologies. The AURORA project aims to merge aircraft and rocket technologies, which is often seen as a straightforward design philosophy. However, this integration is a complex engineering challenge that requires overcoming significant technical hurdles. Many might focus on the end product and the potential for cost-effective space access, but the actual engineering nuances and the potential difficulties in harmonizing aerospace engineering principles are paramount. The significance lies in the fact that successful integration could redefine how space transportation systems are developed, pushing beyond traditional models that often treat aerospace vehicles as entirely separate entities. 2. Budget allocation for advanced propulsion systems. The emphasis on advanced propulsion systems, specifically the development of the AS1 linear aerospike rocket engine, is crucial. While the €50 million budget allocation is highlighted, the complexity and technological risks associated with developing such engines are easily overlooked. Aerospike engines, while promising improved efficiency and performance at varying altitudes, are still in experimental stages. The successful testing and implementation of the AS1 engine could lead to substantial advancements in rocket technology. This investment is significant not only for Polaris but for the entire aerospace sector, as it could pave the way for more efficient launch systems and inspire further innovation in propulsion technologies. 3. Hypersonic Research Vehicle Dual Purpose. The contract awarded to Polaris by BAAINBw for a hypersonic research vehicle is particularly noteworthy. While many reports may focus on this vehicle's potential for defense applications, its dual role as a small satellite launch system should not be underestimated. This dual-use aspect highlights the flexibility and adaptability of the AURORA project, suggesting that it can cater to both military and civilian needs. In a world where the boundaries between military and commercial aerospace are increasingly blurred, this versatility could attract a broader range of investment and interest from various sectors, enhancing the project's viability and potential market reach. 4. Series of demonstrator tests. The series of demonstrator tests, particularly with MIRA 2 and MIRA 3, are critical milestones that may not receive the emphasis they deserve. These tests are not merely stepping stones but are essential for validating the various systems and technologies that will be integral to the AURORA project. Each successful test builds confidence in Polaris's approach and reduces the risks associated with full-scale development. The significance of these demonstrators lies in their ability to provide real-world data and insights that can inform future design decisions, regulatory compliance, and operational procedures, ultimately shaping the trajectory of the project. 5. Long-term vision and market disruption. While the immediate goal is operational deployment by 2025, the long-term vision of Polaris Spaceplanes deserves attention. The goal of disrupting space transportation with a reliable, reusable system could fundamentally alter how space access is perceived and executed. Many readers might overlook the broader implications of this disruption, such as its potential to lower costs, increase the frequency of launches, and democratize access to space for research and commercial endeavors. The broader market disruption could lead to a cascade effect, prompting existing aerospace giants to innovate or adapt their strategies in response to Polaris's advancements. Conclusion. In summary, while the report provides a clear roadmap for the development and deployment of Polaris Spaceplanes' AURORA system, the details that may appear secondary often carry substantial weight. The integration of aircraft and rocket technologies. The focus on advanced propulsion systems, the dual-purpose nature of the hypersonic vehicle, the importance of demonstrator tests, and the long-term market disruption all contribute to a more nuanced understanding of the project. Recognizing the significance of these elements can offer deeper insights into the potential impacts of Polaris on the aerospace industry and the future of space transportation. Here are the 4 most valuable points for in-depth analysis and discussion regarding the implementation of Polaris Spaceplanes' Reusable Launch System by 2025. 1. Integration of advanced propulsion systems. The development of advanced propulsion systems, particularly the AS-1 linear aerospike rocket engine, is a cornerstone of the AURORA project. The aerospike design offers several advantages over traditional rocket engines, including improved efficiency at varying altitudes and speeds. This innovation not only enhances the performance of the spaceplane but also significantly contributes to the vehicle's reusability, a key factor in reducing launch costs and increasing the frequency of space access. The successful in-flight ignition test of the AS-1 engine marks a critical milestone, demonstrating the viability of this technology and paving the way for future testing and refinement. Discussion points. How does the aerospike engine's performance compare to traditional rocket engines in various flight regimes? What challenges does Polaris face in scaling the aerospike engine for full operational capability? What implications does this technology have for the broader aerospace industry, particularly in terms of cost reduction and sustainability? 2. Modular design approach. Polaris's emphasis on a modular design for the AURORA spaceplane offers significant operational flexibility. This design allows for various configurations, enabling the spaceplane to serve multiple purposes, such as a hypersonic transport system or a satellite launch vehicle with an expendable upper stage. Modular design is particularly advantageous for adapting to different mission profiles and customer requirements, enhancing the marketability and utility of the AURORA system. Discussion points. What specific modular components are being developed and how will they contribute to the overall functionality of AURORA? In what ways can modular design facilitate rapid prototyping and iteration during the development phase? How does the modular approach influence the production and operational costs of the spaceplane? 3. Strategic partnerships and contracts. The significant contract from the Federal Office of Bundeswehr Equipment Information Technology and In-Service Support BAAINBw not only provides funding but also positions Polaris at the intersection of commercial aerospace and defense applications. This dual-use potential is crucial for attracting investment and partnerships. Leveraging government interest in hypersonic technologies for defense while also catering to the commercial satellite launch market. Discussion points. How can Polaris effectively balance the requirements and expectations of both defense and commercial sectors? What are the potential risks and benefits of relying on government contracts for funding and development? How does this strategic partnership position Polaris against competitors in the aerospace sector, particularly those focused solely on commercial markets? 4. Validation through demonstrator testing. The series of progressively larger demonstrators MIRA 2 and MIRA 3 serves as a vital pathway for technology validation and risk mitigation. These tests allow Polaris to gather data and refine their technologies before full-scale production. The iterative process of testing and feedback is crucial to ensuring that AURORA meets safety, performance, and reliability standards. Discussion points. What lessons have been learned from the demonstrator tests? And how will they inform the design and development of the AURORA spaceplane? How does the testing phase impact the overall timeline and budget of the project? What role do public and private stakeholders play in supporting or evaluating the outcomes of these tests? Conclusion. The implementation of Polaris Spaceplanes' reusable launch system by 2025 represents a significant advancement in aerospace technology. Focusing on advanced propulsion systems, modular design, strategic partnerships, and rigorous testing processes creates a comprehensive framework for success. Each of these points provides rich avenues for further exploration, discussion, and analysis within the context of the evolving aerospace landscape. 1. Space Shuttle Program. NASA USA. The Space Shuttle program, initiated in the 1970s and operational until 2011, was a landmark in reusable launch systems. It was designed to carry astronauts and cargo to and from low Earth orbit and facilitated numerous missions, including satellite deployments, scientific research, and construction of the International Space Station (ISS). The program faced challenges such as the Challenger disaster in 1986 and the Columbia disaster in 2003, yet it significantly advanced reusable spaceflight technology. The budget for the program was extensive, totaling over $200 billion over its lifetime, highlighting the financial commitment to developing advanced aerospace capabilities. 2. X-15 Program. NASA and U.S. Air Force USA. The X-15 program, conducted in the 1960s, was a series of manned rocket flights that explored the boundaries of hypersonic flight and space travel. The X-15 achieved speeds exceeding Mach 6 and altitudes above 100 kilometers, contributing critical data for future aerospace projects. The program utilized advanced rocket technology and innovative design features, including a reusable aircraft structure. Although not a conventional launch system, the knowledge gained from the X-15 influenced later developments in reusable spacecraft, including the Space Shuttle and modern spaceplanes. 3. Skylon Reaction Engines Ltd. UK. The Skylon project is an ongoing development of a revolutionary spaceplane capable of reaching orbit using air-breathing engines and rocket propulsion. Initially proposed in the early 2000s, Skylon aims to achieve reusable low-cost access to space. The design incorporates advanced technologies such as the Sabre engine, which can operate in both atmospheric and vacuum conditions. Despite facing funding challenges, Skylon has garnered interest for its potential to transform the aerospace industry by providing a more economical and efficient means of launching payloads into orbit, similar to the objectives of Polaris Spaceplanes' AURORA project. Future outlook: predictions for Polaris Spaceplanes' reusable launch system implementation by 2025. Introduction. The ambitious project by Polaris Spaceplanes to implement the AURORA reusable launch system by 2025 is set to redefine space transportation and hypersonic travel. With a budget of €15 million and a structured development strategy, Polaris is poised to capitalize on emerging technologies and market demands. Here are 4 key predictions regarding the project's future trajectory and impact. 1. Successful demonstrator testing and operational readiness. By the end of 2024, Polaris is expected to complete extensive testing of its demonstrators, particularly the MIRA 2 and MIRA 3 models, which serve as prototypes for validating propulsion systems and flight capabilities. Successful in-flight ignition tests of the AS1 linear aerospike engine will likely lead to a series of additional tests, culminating in operational readiness for the full-scale AURORA system by 2025. The completion of these tests will provide critical data and insights that will enhance reliability, safety, and performance metrics, setting a precedent for future reusable launch systems. 2. Strategic partnerships and expanded market opportunities. As Polaris progresses towards deploying the AURORA system, it is anticipated that the company will forge strategic partnerships with government entities and private aerospace companies. The recent contract with the BAAINBw for a hypersonic research vehicle underscores the potential for defense applications, while the dual-use nature of the vehicle could attract commercial satellite operators. By establishing collaborations, Polaris is likely to diversify its revenue streams and enhance its market presence, particularly in Europe and beyond, where demand for satellite launches and hypersonic technology is on the rise. 3. Cost reduction and increased accessibility to space. The development of the AURORA reusable launch system is expected to significantly reduce the cost of access to space. Polaris's focus on reusable technology will likely lead to lower operational costs per launch, making space more accessible to various stakeholders, including researchers, startups, and governments. This shift could catalyze an increase in small satellite launches and facilitate the growth of new space-based services such as Earth observation, telecommunications, and scientific research. The economic viability of the AURORA system may also prompt other aerospace companies to invest in similar technologies, fostering a competitive landscape that could further drive innovation and cost efficiency. 4. Technological advancements and industry impact. The successful implementation of the AURORA system will not only revolutionize Polaris's operational capabilities but also have a broader impact on the aerospace industry. The integration of advanced propulsion systems like the aerospike engine and modular design principles may lead to new standards in vehicle design and efficiency. As Polaris demonstrates the viability of its technologies, it is likely to inspire a wave of innovation across the sector, influencing the development of next-generation space vehicles and hypersonic transport systems worldwide. Conclusion. The future of Polaris Spaceplanes and its AURORA reusable launch system appears promising, with significant milestones expected by 2025. As demonstrator testing progresses and strategic partnerships are established, Polaris is on track to not only achieve operational readiness but also to reshape the landscape of space transportation and hypersonics. The implications of their success could extend far beyond their immediate objectives, influencing the entire aerospace industry and enhancing global access to space.